So m of LE must be a constant multiple, we have written C times m of E. So of course this also works when L has rank strictly less than D, but there we could actually compute what is C, which was 0. Here we will have to work a little bit more to compute what is C. However, there is a bit of a catch here, because we don't know yet whether for an elementary set E, this image L of E is Jordan measurable, and whether we can write m of LE, because if LE is not Jordan measurable, then m of LE doesn't make any sense. So the main important part for the in this case is to show that L of E is in fact Jordan measurable. So for this end, we will make this following claim, that if E is a box, then LE is a compact convex polytope. I will take a closed box here, but it doesn't make much sense, much difference, because you can take the closure of an open box and the Jordan measurability will not be affected. So the claim is that if E is a closed box, then L of E is a compact convex polytope. So to show this, so of course we know that the compact convex polytope is Jordan measurable. So we will finish our proof if we prove this claim for this case. So to show that LE is a compact convex polytope, note that if H C comma V is a half space, so HCV in our notation before, it was the space of points in RD such that the dot product of X with V is less than or equal to C. So here V is an element of RD and C is a real number. So this was our half space, which was given by X dot V less than or equal to C. Then the claim is that L of H CV is equal to the half space H C L inverse transpose of V. So the linear transformation L takes half space to a half space. Here we are assuming that L is invertible, so L inverse transpose makes sense, and this equality means that L takes half spaces to half spaces. So this is pretty straightforward, because if you take, if X is in RD such that X dot V less than or equal to C, then Lx dot L inverse transpose V, this is equal to, by definition of the inner product, X transpose L inverse transpose V. This is the same as X transpose L transpose, and L inverse transpose is L transpose inverse V, and this is this identity. So this is X transpose V, and this is just the dot product of X and V, and this is less than or equal to C. So the image of the half space, which is given by L of X, where X is in the half space HCV, so here X belongs to HCV, then L of X satisfies this inequality, where Lx with the dot product L inverse transpose of V is again less than or equal to C. So it takes a half space to a half space. And now, since a compact convex polytope, let me call it M. Let M be a compact convex polytope. Then M can be written as the intersection of finitely many half spaces I equal to 1 to n H C I V I. So L of M is then L of this intersection H C I V I, and this is intersection of L H C I V I, and here I am going I've again used the invertibility of L, because in general this is not true. It's only true when L is injective, because this intersection of the image is the image of the intersection can only be true when L is injective. In this case, L is in fact invertible, so this equality holds. And we know that this is for each I, we have H, L of HCI VI is HCI L inverse transpose VI. And this is again a compact convex polytope. This is an intersection, finitely many intersections of half spaces, so this is a compact convex polytope. So in fact, L takes a compact convex polytope to a compact convex polytope, and since a box in itself is a compact convex polytope, then the image of the box will again be a compact convex polytope. So we have shown that if E is a closed box, then LE is a compact convex polytope. Now, this shows that in fact if E is an elementary set, then LE is Jordan measurable. So this implies that if E is elementary in RD, then L of E is Jordan measurable, because if E is a disjoint union of boxes BI I equal to 1 to M, say, then LE is the union of LBI I equal to 1 to M, and this is a finite union of compact convex polytopes, so this is Jordan measurable. This is Jordan measurable. So in this way we have proved that if E is an elementary set, then LE is Jordan measurable, and M of LE is C times M of E for some constant C greater than 0. Well, for the moment it's greater than or equal to 0, because we don't know whether C is 0 or not, but we will find out that if determinant of if L is invertible, then determinant of L is not 0, and C is just the mod, it should be the modulus of the determinant. So we will prove that later. So this proves the first part of the theorem. The second part says that if, so this is what we want to prove, that if E is Jordan measurable, then LE is Jordan measurable, and again the same relation holds, that M of LE is equal to C times M of E. So to show this, let epsilon greater than 0 be given, and we choose an elementary set A, a subset of E, such that Mj lower subscript j, which means that we are taking the inner Jordan inner measure, the Jordan inner measure of E is less than or equal to Ma plus epsilon. Then the image of A is a subset of the image of E, and so the elementary measure, the Jordan measure of LA is no longer elementary, so we can only talk about the Jordan measure because it's a compact convex polytope, or a union of compact convex polytopes. Nevertheless, it is Jordan measurable, but M of LA is less than or equal to the inner Jordan measure of LE simply by monotonicity. But we know that M of LA is C times M of A because A is elementary, and so this is less than or equal to the inner Jordan measure of LE, and this implies that because MA is greater than or equal to MJ, the inner Jordan measure of E, minus epsilon, so the inner Jordan measure of E minus epsilon is less than or equal to the inner Jordan measure of LE, which means that CMJ, or actually it's just M of E because E is Jordan measurable, minus C epsilon is less than or equal to the inner Jordan measure of LE. Similarly, one can show using the outer Jordan measure that the outer Jordan measure of LE is less than or equal to CME plus C epsilon. So we will get a chain of inequalities. CME minus C epsilon is less than or equal to the inner Jordan measure of LE is less than or equal to the outer Jordan measure of LE and is less than or equal to CME plus C epsilon. Now, since C is a constant independent of E, it is independent of epsilon, which means that C epsilon is arbitrary, and therefore this implies that the inner Jordan measure of LE is equal to the outer Jordan measure of LE is equal to C of ME. So in particular, these two things are equal and LE is Jordan measurable, and we have proved in the same statement that it is equal to C times M of E, where C is the same constant that was used in part 1. Lastly, we have to show that the third part claim that C is equal to the modulus of the determinant of L. So for this, we again need some facts from linear algebra, which is that if this is a fact, if L is invertible, then it can be written as L equals U times P, where U is an orthogonal matrix, and P is a positive definite. So this is in particular a real symmetric matrix. So we can use this factorization to prove that C is in fact equal to the modulus of the determinant of L. So first, if U, okay, so we will use this fact that M of L1, L2 of E, so if L1, L2 are linear transformations, then if L1 and L2 are linear transformations, then M of L1, L2 E, so the multiplication of L1, L2, matrix multiplication, this is C1, C2 M of E, where M of L1 E equals C1 ME and M of L2 E equals C2 ME. So this can be very easily checked. So check this claim, and it follows straightforward from these two facts. So if L is equal to U multiplied by P, then we have determinant of L is determinant of U multiplied by determinant of P, and the modulus is the multiplication of the modulus, but the modulus of the determinant of an orthogonal matrix, this is equal to 1, and so we are only left with this part, determinant of P, where P is a positive definite real symmetric matrix. Now we can further decompose P as Q transpose DQ, where Q is again an orthogonal matrix, and D is a diagonal matrix. So this is about diagonalization of invertible real symmetric matrices. Of course, if L is invertible, then P is also invertible in this so-called polar decomposition. So this is the polar decomposition. So again we are left with an orthogonal matrix Q and a diagonal matrix D. So it's enough to check the formula for C when your linear transformation is an orthogonal matrix, in which case C should give you 1, and when it is a real diagonal matrix, in which case it should give you the multiplication of the diagonal elements and taking the modulus of it. So I will leave the diagonal part as an exercise. So check that M of DE is equal to the multiplication lambda 1, lambda 2, lambda D modulus M of E, where D is the diagonal matrix lambda 1, lambda 2, lambda D, and other entries are 0. So remember that this constant C was M prime when we defined another map on the elementary subsets of RD to the positive reals. Then this was simply the measure of the unit box, d-dimensional unit box 0, 1 to the D. So this in our case we had the multiplication, we had the linear transformation L. So we just have to compute the measure of the image of the d-dimensional unit cube under the linear transformation L. So it's quite easy to compute what is the measure in case D is the diagonal matrix lambda 1, lambda 2 up to lambda D, because it will scale each coordinate with the lambda i's. So then we will have the modulus of the product lambda 1, lambda 2 up to lambda D. It will still be a box. So in this case, when D is a diagonal matrix, then the image will still be a box. So here L is our D, and in this case this will be simply modulus of lambda 1, lambda 2, lambda D. Now in case L is equal to L is an orthogonal matrix, then take E to be the unit ball, closed unit ball centered at 0 with radius 1. So in this case an orthogonal matrix preserves the unit ball, because L is an isometry of RD and it preserves the dot products. So since L preserves dot products, we have L of E, L of the closed unit ball is the same as E itself. So then we have M of LE is equal to M of E, and this can be written as 1 times M of E, and of course 1 here is the determinant of L, because the modulus of the determinant of L, because L is an orthogonal transformation. So in this case we can also check that our formula holds, that C is the modulus of the determinant of our linear transformation. And this will conclude our proof, because once we have checked it for orthogonal matrices and for real symmetric matrices, then our polar decomposition will ensure that the constant C is given by the determinant of L, where we can use now the multiplicativity of the determinant.